Because to start or oh, okay. Now I'm just writing the SAIFR words we had before. So now I just wrote again what we were talking about before. So we derived this form of the 2pi effective action, right, which depends only on our dynamical degrees of freedom. We derived the form of the fluctuations, and we said, okay, to the first order corrections in H bar, so quantum fluctuations, we're going to have these two diagrams. And then by looking at the stationary conditions for this action, so the functional differentiation with respect to G, we got Schwinger-Dyson equation. Okay? This is already what we wanted to have. We want the equation. Now we just need to rearrange it a little bit, and this is already going to be our equation of motion for the propagator. Why? Because as you see inside this G0, and this comes from the beginning, from the differentiation of a full action, here is our time derivative, right? So now we just need to rearrange it around to get a nice time evolution equation. Okay, so what do we do? If I want it to be very detailed, right? I need to do convolutions from the left, convolution from the right, and so on and so forth, right? So in principle, what I need to do is, okay, so I'm gonna have G0. Oh no, it's not what I want. Okay, so I multiply with, I convolute with G from this side, so from the right. So I'm getting an identity, which actually in our world, identity is the delta on the contour T minus T prime equals to d T, and now this is, okay, let's say it's gonna be T1 minus T2. Now it's gonna be dt G0 minus 1 T1 P g t t2 minus t1 g t t2. Right? Make sense? Okay, so now there are going to be a lot of simplifications. First, and this is all the time we're still on the Keldysh contour. First, when we plug in the form of G0, we already see that this is going to be a time local term. This entire time integral is going to disappear. Right? Then we're also going to have derivative term acting on our G. From sigma acting on G, again, we have one term where the integral disappears, and one term where it's going to stay. So when we put it all together, what we get minus I dt1 squared g 2 I'm definitely going to on some sides. And this guy as well. So possibly plus 4g t. This all acting on our g t1 t1 and our g t1 2 plus contour integral over the remaining part of the self-energy. So I'm going to call this guy sigma hat. Now, okay, so what happened here? We had our full propagator. We want to know what are the equations of motion, right? It depends, the equation for its time evolution depends on some bare propagator, local guy. This local guy contributed in my equation of motion, contributed this derivative. This is from the bare propagator and these two guys, right? Then I have also the self-energy. Where does the self-energy come from? What is this guy? Which diagram?
This comes from a loop.
This comes from cutting this guy. This is BAM. You remember? Because the self-energy equals to the derivative respect to G. So this guy is cutting this diagram. That's why it gives me time local contribution. That's why in the equation there is delta, because I have only one time here. So when I put it under the integral, this guy is here. This was also what we were talking about in terms of, okay, if I was doing weak coupling expansion, I would only have time local terms, and I could get it from Heisenberg equations of motion. Because up to here, right, these equations, here I have GT1, T2, and all of these other guys depend only on the same times, right? The first line, everything is the same point of time. It doesn't depend on a history. But now, because we have this additional diagram, and this guy is this expression, because it's going to give us the guy with happy hands. This guy is going to produce this contribution, and this is a memory kernel. So what effectively the non-perturbative effects we want to capture within the time evolution, how they appear in the equations of motion, they appear via this memory kernel. So now we have, now if you want to solve it, you have to integrate over the history to compensate for your lack of knowledge due to the truncation of the expansion. Does that make sense?
Yes.
It does?
About.
More or less. Okay, good. It's okay, but you see, one could think that we are more or less done, right? We have a differential equation of motion thing. So how do I solve this guy? I mean, how do you solve the differential equations? I give you, you take your favorite differential equation. What do you do with it?
Forward with that.
Sorry?
Separating the variables.
Very complicated options. I would think like you find your favorite Python library, you plug it in, and you see the result, right?
Okay.
I would think that would be the third option, okay? Why I cannot plug it into my favorite numerical function?
Because you don't have initial variables.
Initial state, I'm gonna, I can say, this is my initial state, whatever state I'm interested in, whatever state I want to study, and, I'm gonna evolve it. So I can come up with initial state. That's fine. But this guy depends only on G functions and everything, so I can compute. It depends on the propagator. I just compute it at every stage, right?
No, G.
But this is the equation for G, right? So why? It's not, if I numerically discretize it, in principle, there's no problem for me to compute the solution.
The evolution of the mean of X.
This guy, I do it alongside G. I just have two coupled equations, no problem.
So you need like all the values before to the next value.
Yeah, which is annoying computationally, but I can do it. I can always, at every step of the propagation, I can go all the way back.
So there's no problem.
The delta function. Okay.
Okay, I'll show you where's the problem. We're still on the Keldysh contour. And how do I put the Keldysh contour? How do I parameterize Keldysh contour? How do I plug it into a computer? This is what we have to deal with. Apart from the fact that also, which I didn't write down yet, this is an equal time Green's function. But here is just partial derivative with respect to the first time. So actually, how do you need to propagate your, when I do my discretization numerically, right? For every time step, I have to consider what are the time steps in first time direction and the second time direction, right? I have two time arguments. But fortunately, getting an equation for the second time argument is, once you get to this one, it's almost trivial, because what you do, you basically, instead of convoluting with G from here, we got T1. Instead of convoluting from the right, we do the same procedure and we convolute from the left. Okay? What does it produce? Effectively, it produces additional minus signs, because if you think about it, this is some derivative. So when you do differential by parts, so it acts in the opposite direction, you get minus signs. So the equation of motion for propagation in T2 is just minus this guy. Yeah. So now you have to remember you have two coupled equations. So I'm going to concentrate on this one, but everything applies to the other one as well. In principle, you have to solve both of them at the same time. Okay. So what do we do with our favorite Keldysh contour? The thing is about Keldysh, what to do with it, there's a you saw already yesterday, there's an entire zoo of greens functions, right? You can define this retarded, advanced, and so on and so forth. Not to complicate matters further, I'm going to define two more. There is a method to this madness because they are going to also appear in the next lecture by Aleksandra, and they have some physical interpretation, okay? So I'm going to introduce these two new greens functions, the so-called spectral. This is a spectral function, which equals to 5 times. I mean, these are my variations. And statistical. It's commutator and anti-commutator. And why are they called? More or less, and for now, if we have time, I will show you a bit more how to justify this physical interpretation. But more or less, because this tells me what's the spectrum of my excitations. And so what are the available states in the theory, like in general? And this guy tells me, once I have the available states, how am I distributing the actual excitations within the available states? That's why the nomenclature. Just for if someone really likes the language of Keldysh and retarded fractions, this is actually the Keldysh one. This is the Keldysh guy, and this guy is a sum of retarded and advanced. Now, yeah.
I just want to say something because yesterday you were indeed eager to know what you have to know about Keldysh. I think you can approach here the course in a very pragmatic way. If you understand what Aleksandra is saying by the end of today, with air definitions, then you're in business. You can basically forget about that. Can you expect us that if we expect the time to but really it's like will not repeat this to you. So if by the end of today what she says makes sense to you with her definitions, which of course somehow requires my definition, and you need to know what is GR, that probably you knew already, then you don't need to worry about testing. Pragmatic approach.
Okay, so now how do we decompose our Green's function on the Keldysh contour? This is the definition. That's contour ordered two fields, right? And what does it effectively imply? It means that, and now there's a theta function on the contour, right? That if t is larger than t prime, then on my state, first acts the guy with t prime, and then acts the guy with t. Right? If you remember, when we were constructing the path integral, here's some state, alpha, so we act from this side. So here's the first one, second one, third one, so on and so forth. So that's like the earlier one is here. The earlier one's on the right, and this is plus theta c, and the opposite. They have the opposite ordering. If there's a different, right? So far, so good. I mean, nothing, I didn't write anything crazy, I think, yeah. All right. So, any questions? Okay, actually, a small quiz at this point. This is my Keldysh contour. This is time 1. This is time 2. Which one is larger? Sorry?
Teacher.
Yeah, right? Larger than 2-1. This wasn't a trick question. You're just comparing two things, right? Okay, now the trick question. Which one is larger, T1 or T2?
Two.
In the contour set, it's T2. From a perspective of this time ordering, it doesn't matter that this contour is somehow going back, as far as this time ordering is concerned, we could be doing a contour on a spiral, right? The only thing that matters is that this guy goes here. So this point is after this point, then this point, then this point. It goes in this direction, okay? In terms of contour ordering, this is the only thing that matters. Eventually, what you want to recover from the contour ordering is how does this translate into the linear ordering, right? And linear ordering will be where are these guys here, okay? But for now, we're just with contour ordering. Good. So now when we have that, we can add and subtract the same thing, so add 0, so that we have, okay, there's a lot of zeros to add, subtract. That matter of adding with the same theta function, I'm adding these guys in the opposite, I'm subtracting these guys in the opposite direction and adding them with the opposite direction. What I'm gonna end up with is commutator and anti-commutator, right? Because I'm subtracting, adding the same thing. So what's gonna be is precisely our statistical y here is going to be the theta disappears because we already because it's going to in front of here is gonna be theta c, right, plus what is it? 1, right? Either way, something happens. So that's why we don't write it explicitly, right? But in front of the other guy, we're going to have, and now so I don't mess it up, theta c minus 1 minus so there's a minus sign here, right? Because one of them subtracted that and so on and so forth. This guy is sine in a contour sense, t minus, right? So these guys are giving me a difference of a minus sign depending which of the time arguments is larger. But you see, so already at this level, I got the representation of this function, and I effectively got rid of this time ordering, implicit time ordering. The only remnant of my contour is this guy. Okay? But now we'll see that actually, if we when we plug it into the equations of motion, we are going to get something which is independent of that. And then whether I will manage to plug it in, that's the question. Okay. This decomposition applies to the propagator, but the same decomposition applies to the self-energy. So this guy, sigma hat, is also going to be some statistical sigma. That's same decomposition. And then the only thing we're doing is plugging it in. So how does that look like? It looks rather awful, but we'll go through this pain once, and then you're going to see the structure of the equations, okay? So we are plugging these two decompositions into this equation. In principle, you have to do it also for the other time argument. Okay, so we do left-hand side, meaning plugging here. What do we get on the left-hand side? Minus T1 squared Fi minus minus 2 squared rho 1 2 plus 2. What happened here? Right? Okay, applying the derivatives to f, easy. But then I have to apply derivative to this term, right? When I have both sine and rho. I use the normal distributive property of the derivative. And I use the fact that, right, this guy inside, these are theta functions. And I know how to take derivatives of theta functions, right? It's just deltas. So actually, so one thing you can think of it, so the useful identity, which I mean you can derive yourself within a second, minus 4, but the derivative is 2 times delta. Yeah. Okay. This is the left hand side. It's ugly, but just what it is. Right hand side. So delta C 2. I am going to call this guy, because I can't be bothered to write it over again, and it's not particularly insightful. This term, so this is some time local term. Oh, sorry. This is omega P1. Good. It depends only on one time argument. So I have minus I omega P1 times the propagator these horrible integral terms. So again, I have, for now, I have the integral over, still over the contour time. But now already, you should see what is going to help us with dealing with this contour time. Any enlightened guesses? Well, what is any other function which is inside the integral, which depends on the contour?
the sign.
Exactly. So this sign is what's going to help us deal with the contour and select only a linear part of it. Okay? So how? So first of all, left and right hand side, actually this guy goes away. Right? And another thing, this term, which is without any signs, this is some function. This is the integral of the type contour d tau, some function of tau. Right? When I multiply this guy by this guy. If the contour is closed, and this is an analytic function, and there are no poles, what's the result of this integral?
0.
Yes, exactly. Bam, okay? One term disappeared. We're good. So it's getting slightly easier, right? So don't remove something that we will desperately gonna need in a second. Okay, so now what's also nice that all of these functions here, they are real functions. So actually we can take from left and right hand side only the imaginary part, only the real part, and solve them separately. Okay, so let me say, so first we take the real part. So on one side, we have sine c 1 minus 2 there, which equals to our t row t1 2, and also sine c plus okay, I started writing more and more horrible handwriting, so I hope that I'm still legible. The nice thing you can notice about the separation is actually the dynamics of the spectral part decoupled from the statistical. You see, all of the quantities in this equation depend only on rho or sigma rho. And that makes sense, right? Because spectrum is somehow more inherent in the theory. What are my available states shouldn't depend on the statistics of the problem. On the other hand, the equation for f, for the statistical part, will depend on rho. Because to know how I'm going to occupy states, I need to know what states are available. Okay? So this is the structure we actually expect. And what is the guy we don't like? The one with lots of signs under the contour integral that no one knows what to do with, right? Okay, but fear not, we shall consider it. Okay, so how do I solve a contour integral of 1 minus tau of this type? When it's some function of tau. Let us first consider a case when tau1 is greater than, time 1 is greater than time 2. Right? In this case, I draw my contour. I have some contour. Let's say, so time t1 is greater. So I'm saying, okay, this is t1, this is t2. Is this t1 greater in the contour sense?
Yes.
Exactly. Okay, this is greater in the contour sense. Good. And now, how do we solve this integral with respect to, what are these signs in the contour? We just separate it into a couple of sectors. So when I go here from 0, let's say this is 0, I go 0 to t2. So this is my first one. in my first element from 0 to t2, this is simply just an integral from, this is a line integral from 0 to t2 over d tau. So now it's already a line element. And what are these signs? Is t1 greater than tau on this sector?
Yes.
Is tau greater than t2 in this sector?
True.
So it's going to be minus
Yeah.
f of tau. Then, sector 2. We go from here to here. This bit, it's from t2 to some t star, and from t star to 2. This is going to cancel out. So the only thing I have is line integral from here, from my t2, like, mirror t2 to here. So this is an integral from t2 to t1, now in a line sense, v tau. And again, look at this guy, right? Tau is still smaller than t1, but now became bigger than t2. So this is going to be on the plus. And then what I have, the third sector, this is just an integral from line integral from t1 to 0. From t1 to 0, and here, this guy gives me a minus. So it's minus f of tau. So now I can add up these guys, right? Now they're just line integrals, I have to like flip the limits, there are some minuses. And after I add them up, I get just 2 times t2, t1, d tau, f tau. This is for t1 greater than t2. Now you can repeat the same analysis for t2 greater than t1. Spoiler alert, you're gonna get minus what you got now. But, so here you're gonna get minus, but these guys are also gonna be minus and minus. So actually equation is gonna be the same in both cases, right? So now in the case that we consider here t1 greater than t2, this is a plus, that guy is a plus. We just wrote that this guy is 2 times this integral. So we can pull all of this together. If I find a space on the board. Okay, this guy is gone. All of this together, and we get equation for the spectral component. This is what's this? Now, can I solve this equation?
Sure.
I think so too. Yeah. So now this is okay. This is actually the end of our suffering, at least, if we're talking about spectral function, right? So we already, after all of this, painful thing, we actually got an equation of motion in terms of linear time. So we can put in a computer for our 2-point function with quantum fluctuations in a self-consistent variational approximation, which can capture non-perturbative effects in non-equilibrium physics, okay? Just be excited. It was painful, but we got here. We have it, right? And this is already something you can solve. I mean, but now you have to go to the other guy. Now there's not all the pain. So now you have to consider the imaginary part of this guy and find the equation for f. So it's a little bit more pain still. But the equation, so again, I'm taking the imaginary bit here. And now I'm a bit, okay, so it's gonna be this guy, and these cross terms. Now you're gonna see that the equation of motion for F, for the statistical guy, is going to depend on rho and on sigma rho. Here the integrals are gonna be a bit easier because here's only one sine function. So one sine function basically is going to mean that when I do I have to care only with respect to one time. So for example, when I look at the sine with respect to T1, I'm going to get, okay, I have some integral from 0 to T1. This guy cancels out because it's the same thing. And then here I'm gonna have a minus the integral, but with opposite integration signs, right? So I'm gonna have something 0 to T1 detail minus T1 0 detail. Yeah?
Yep.
So I'm gonna have twice the same thing. So this twice the same thing is going to replace my signs here and get rid of these twos actually. And I'm gonna write for you the final expression because it's a bit painful to write it out, all of it. And we get so a bit longer expression, but still, in terms of linear time, so I can plug it in the computer. It depends on rho, but I already know how to solve for rho as well. So these are just simultaneous differential equations. The main difficulty, of course, comes from integrating over memory kernels. But I mean, there's no free lunch. We have to pay a price for capturing these higher order effects. Questions?
Where is lambda?
Yes, it's hidden. So lambda, and of course, I already erased thing. Lambda sits in these sigmas. Because what is lambda? Lambda is the interaction. So in our expression for gamma to pi, it was this higher order effect. And sigma is the I gamma 2 in G. So this guy is the interactions. So this guy has lambdas. So this guy inherits lambdas from him. Right? So effectively, what is sitting here? What is sitting here is this diagram. Is this diagram because we removed the time local part, and actually time local part is hidden here. So this guy now is hiding here. Right? Just because it's time local, so it escaped the integral. More questions?
I like the intuition that you gave us that this equation, the equation to the spectral function, is decoupled from the statistical function, because in some sense you have the system and its spectral properties may not depend on statistical things, but
They shouldn't, yeah.
it is general. Like if I have a system coupled to a map, these equations are gonna be decoupled also is a general thing. Like to have the statistical.
I would think that it should, I would think that they should be decoupled. No, they're not
Sigma rho depends on that.
for a thing. Okay,
So the equations are complicated.
Also consider that this one is a very special example, since 1 because of freedom.
Yeah.
And when you have an extended system, there is an approximation called positive particle approximation that you do on purpose in order to do what is happening in the example and what we want. to
Okay.
do.
Because I was thinking that this is decoupled by the fact that this is a closed system in the sense that we are looking to all degrees of freedoms in a unitary kind of evolution.
But
So maybe it's possible to have something more complex, even in the Hamiltonian case.
just in the Newton case, one intuitive way to understand this is you remember yesterday we were talking about the delta Dirac and the Laurentian. Now, in a closed system, the width of the Laurentian, the lifetime of a quasi-particle will come from the scattering against the other particles in the system. But the scattering rate will depend how these are occupied. So the spectral property will know about the occupation. I confusing you,
No, not that much.
not that much.
Yeah.
So you have an isolated system. Imagine that there is a particle traveling in this journey in the system, 3 particles. Okay, everything is nice. Its spectral function is identical. Now all of a sudden you switch on interactions in this mental experiment, and these particles scatter against other particles. Fermi Golden rule at a certain point, she will develop a lifetime and decay into other duality. Right? This lifetime will depend on how the other particles are occupied, how many there are, right? Because if it is diffuse, the broadening will be very small. If it is very dense with many other excitations, the broadening will be finite. But diffuse dense means statistical properties in the language of Aleksandra, how stuff is occupied. And so in a real situation, even unitary, even isolated, the broadening will know how stuff is distributed. And that's why people sometimes do this thing that I mentioned, quasi-particle approximation, that to say, you know what, I don't care. Broadening is 0, always. I have a well-defined quasi-particle, I don't care, and I only will look at how the statistical function evolves. And it's, but it's a broadening approximation.
okay. So I guess maybe I'll expand on it a little bit more. I don't know how much. Plenty. Yeah. Slide. Okay. Okay. So now, just to get a little bit more intuition of what are the statistical and spectral components, actually, for a second, let us go away from our complicated non-equilibrium stuff and think about equilibrium situation. And I think that could maybe clarify a little bit. So what happens in thermal equilibrium? Thermal equilibrium, in thermal equilibrium, we have time, we have time translation invariance, right? So now all our functions, instead of being the functions of t and t prime, are just a function of the difference of them. So I can write them that in equilibrium is equals to Fourier transform I like t equilibrium omega, and similarly with the other guy. There you go. And also another aspect, what do we have in equilibrium? Instead of thinking about time evolution, we can think about, we have thermal averages, right? Of our operators. Now we can think about this generator almost as a generator, as a propagator in imaginary time. Right? This looks a little bit like the IHT. So instead of, and this is actually TC. So instead of ITC, we have beta on our Keldysh contour. So now, when we go from along the contour, we go from time 0 to time, I think beta, I beta, I think I should write it. Yeah. Minus I beta. Imaginary time propagation, okay? And now, but these points have to be physically the same, right? Because, I mean, I should be able to squash my contour. So what does it mean for this guy? On one side, if I write it in terms of these Fourier transformed quantities, at this point, I have that F equilibrium omega plus I have rho equilibrium omega, right? What do I have on the other side? It's a propagation by minus the difference in the, here I'm gonna have time is gonna be minus beta omega, right? So go all the way to the other side. Equals to minus beta omega. And now F is the same, but the sign acquires the opposite, where's the opposite sign? The sign function. So far, so good? Equating these 2 points. Where's the magic in this expression? And this is only applies in equilibrium. And rearrange them, not particularly difficult. And what I get, what does this look like? First of all, how does this guy look like? Bose-Einstein distribution, right? So this expression is basically your fluctuation dissipation theorem. So you have the relation with the statistic, the occupation of the states equals to minus I, the distribution function times the available spectrum. So in this sense, you see available states times how they're, this function tells me how I'm firmly occupying them. And this tells me the statistics, the overall, like, where am I occupied? Does that make sense?
Strong assumption.
What strong assumption?
Making sense.
So, okay, important, this holds only in equilibrium, okay? So in principle, it doesn't hold in out of equilibrium, and the 2PI formalism actually covers broader range of situations. So this having this sort of only as a special case in equilibrium. Yes?
We have words.
I don't see why not, as long as it's equilibrium.
At room temperature, at high temperature.
I don't see why not, right? Because it's also, I mean, you know, like for high temperatures, the Bose-Einstein distribution becomes a Boltzmann distribution, right? So that is the distribution of classical particles, and it's. That's what's true.
Well, the formalism does work well in high temperature vortex, like in Brian.
I'm not sure that. I don't immediately see the problem, but I also not sure whether I've seen situations like that, so I don't think I can comment really well on that.
I mean, also like, if I may, the notion of like high and low temperatures, right? I mean, it's like in physics, there is no such thing as like 300 Kelvin can be extremely high for certain systems and extremely low for other systems, right? So there is like, you know, also from this point of view, right? So like it depends on like what are the other, let's say, energy scales, right, of the system, right? So like it, you know, from this perspective already, sort of like there is no, let's say, magical temperature, let's say 500 Kelvin above which it would break down, right? Because 500 Kelvin means like nothing really, right? So let's say ultra-atomic system 500 Kelvin, but like for, let's say, quark-gluon plasma 500 Kelvin is extremely chill, right? So, and in both cases, actually, this the so-called mass water formalism is heavily applied.
And maybe this question is, who has never heard about fluctuation dissipation theory? Who has not? Okay.
I think actually that's it for me. I think from this point we are ready to do Dicke model, right? That this is the main takeaway, that after a bit of pain you can derive these equations, but in terms of practical computations, you would already start from the form of the gamma to pi, this 2pi effective action. You would write down the diagrams by knowing the symmetries of the problem, and knowing that they have to be two-particle irreducible, and you would start from that point to derive your equations of motions, which need to be solved. And I think maybe we'll take a coffee break before doing the next bit.
Yeah. Basically,
I'm very organized.
something is going out of.
Yeah, of course.
Example, enter way we can solve it. If you turn if all times we turn, we want to know for the one. So we already have some. It's like we have to know. We want to
Yes,
see,
correct.
but
Then we
for
have it.
calculate this,
And that
we already have to
But
know.
that is for on this level.
Not really, if you think about it, because this tells me that I need to know G. Actually, effectively, what you're gonna see, you only know G at earlier times, right? So you don't need to know the future. You only know, you need to know your past, which actually it's naturally occurring causality which comes out of it, right? Because this is how physics work, right? In a lot of situations, we need to know in what state was I before to know where am I going to go next.
This quantum?
Yeah.
You have, for example, like an epsilon.
In a way, yeah, because effectively these are these 2 points are the same.
Okay.
We write them apart just because it's would be hard to say like, okay, it's lying back forth, right? Yes,
Okay.
exactly. Yeah.
We talk about the differential between the statistical part from the spectral part. In general, with but it's not true, right? But
Then there is some back action, yeah, for equations with them. I think you're gonna see it because these equations. So now without all of these previous derivations,
Okay.
Alexander is going to derive these equations for an open system.
okay, yeah, okay, but with a different Hamilton, but a closed system, because all the system
I-
was with the like,
Yeah.
lambda.
Yeah. I've never seen for unitary systems without noise. I've never seen these.
So I would think it should work, like.
Exactly,
Yes,
like
the
I've
spectrum
never seen it
separated.
for unitary systems without noise.
Mhm.
That's like, I mean, all the time I've seen it like row always
That's
the
nice.
couples. I think that's why I'm saying, maybe
Okay,
with noise,
okay,
there's
but-
some problem, but
But. I can't everything now, because we saw that we can model a system with a jump operator sigma y
yeah.
as a closed system with noise.
Exactly, that's what I mean. So that's why like if there's noise or there are jump operators, I think then this doesn't necessarily hold.
Okay, okay, but this noise is just should be real noise with the properties of the mean is zero and the variance different from zero, or can be a function of time just.
I think, okay, in principle, you can add any noise you want, right? But now if it's a complicated noise, you're gonna complicate your calculations a lot, and it's not clear what's the physical motivation behind it.
Yeah, well, just to.
Right? And then somehow how this noise looks like, depending on case by case basis, almost you're gonna, it's gonna appear differently. So that's why it's hard for me to say, make a general statement.
Okay. Other question? Here, you said that this is like a fluctuation dissipation term.
Fluctuation dissipation theorem.
Where can I find here details balance? Like,
So detail, yeah, so I mean, effectively, this is the statement of I would say this is the statement of the detail balance, right?
yes, it is. It look.
Exactly, like I would say so, but this applies only in equilibrium.
This. This is the citation. It's a little different, but the detail balance within fluctuation expression. System.
Yeah. Yeah, I think it's probably like, I mean, basically saying this is like this is detail balance and then fluctuation dissipation follows. There's some question on the
Statistical mechanics. The rainbow.